Imagine a tiny compass needle, far smaller than the eye can see. This needle represents the nucleus of an atom, the heart of matter. Just like a compass needle aligns itself with Earth's magnetic field, atomic nuclei also have a property called spin that makes them behave like tiny magnets. Nuclear magnetic resonance, or NMR, is a powerful technique that exploits this property to study molecules. NMR is like listening to the faint whispers of atoms and molecules. By applying radio waves to a sample placed in a strong magnetic field, we can make the nuclei resonate or vibrate at specific frequencies. These frequencies act like fingerprints, revealing the structure and dynamics of the molecules under investigation. NMR has revolutionized our understanding of chemistry, biology, and medicine. It allows us to determine the structures of complex molecules, study chemical reactions in real time, and even image the human body without harmful X-rays. The discovery of NMR was a triumph of human ingenuity, opening up new frontiers in scientific exploration. In the early days of NMR, scientists used a technique called continuous wave NMR, or CW-NMR, to unravel the secrets of molecules. Imagine a radio tuner slowly scanning through a range of frequencies, searching for a station. CW-NMR works in a similar way. In CW-NMR, a radio wave is continuously applied to the sample, while the magnetic field is slowly swept through a range of values. When the frequency of the radio wave matches the resonance frequency of a particular nucleus in the sample, a signal is detected. This signal appears as a peak on a graph, revealing the presence of that specific nucleus. CW-NMR was a groundbreaking technique, but it had its limitations. It was relatively slow and insensitive, requiring large amounts of sample and long experimental times. However, it laid the foundation for the development of more sophisticated NMR techniques that have revolutionized the field. Let's dive deeper into the mechanism of CW-NMR. Imagine a group of spinning nuclei, all aligned with the external magnetic field. These nuclei are like tiny gyroscopes, precessing at a specific frequency determined by the strength of the magnetic field. When a radio wave with the same frequency as the precessing nuclei is applied, it interacts with the nuclei, causing them to absorb energy and tip away from their aligned state. This absorption of energy is what we detect as an NMR signal. As the magnetic field is swept in CW-NMR, the resonance frequency of different nuclei is brought into alignment with the frequency of the radio wave. This is why we see multiple peaks in an NMR spectrum, each peak corresponding to a different type of nucleus in the molecule. Despite its limitations, CW-NMR played a crucial role in the early development of NMR spectroscopy. It provided valuable insights into the structure and dynamics of molecules, paving the way for more advanced techniques. While CW-NMR is no longer widely used in research, it remains an important educational tool for understanding the fundamental principles of NMR. Its simplicity allows students to grasp the basic concepts of nuclear spin, resonance, and magnetic field interactions. The legacy of CW-NMR lives on in the more sophisticated NMR techniques used today, such as pulsed Fourier transform NMR or FT-NMR. These techniques have revolutionized fields ranging from chemistry and biology to medicine and materials science, demonstrating the enduring power of NMR as an analytical tool.